Welcome to our lecture on vector-valued functions and space curves. In this video, we'll explore how to describe curves in three-dimensional space using vector-valued functions, calculate their arc length, understand curvature, and analyze motion along these curves. Let's begin by understanding what vector-valued functions are and how they relate to space curves. A vector-valued function in space assigns to each real parameter t a vector in three-dimensional space. We write R of t equals the vector with components x of t, y of t, and z of t, where x of t, y of t, and z of t are ordinary real-valued functions of t. As the parameter t varies, the tip of the vector R of t traces out what we call a space curve. Think of t as time, and imagine the tip of our vector moving through space as time progresses. Let's look at our first example, the helix. Consider the vector-valued function, R of t equals the vector with components cosine of t, sine of t, and t, where t ranges from 0 to 4 pi. What does this curve look like? If we look at just the x and y components, we have cosine of t and sine of t. This traces out a circle of radius 1 in the xy plane. Meanwhile, the z component is simply t, which increases linearly with t. So as t increases, our point moves in a circle in the xy plane while steadily rising along the z-axis. This creates a helix that wraps twice around the z-axis, since t goes from 0 to 4 pi, which is 2 complete rotations. Now, let's move on to calculating the arc length of a space curve. The length of a curve R of t from t equals a to t equals b is given by the integral from a to b of the magnitude of R prime of t dt. Here, R prime of t is the derivative vector with components x prime of t, y prime of t, and z prime of t. And the magnitude of R prime of t is the square root of the sum of squares of these components. Intuitively, we're adding up the infinitesimal distances traveled along the curve. The magnitude of R prime of t gives us the instantaneous speed of movement along the curve. And when we integrate this over the interval from a to b, we get the total distance traveled. Let's calculate the arc length of our helix example. For R of t equals cosine of t, sine of t, t, we first need to find R prime of t. Taking the derivative of each component, we get R prime of t equals negative sine of t cosine of t, 1. Next, we compute the magnitude of R prime of t, which is the square root of sine squared of t plus cosine squared of t plus 1 squared. Since sine squared plus cosine squared equals 1, this simplifies to the square root of 2. Therefore, the arc length from t equals 0 to t equals 4 pi is the integral from 0 to 4 pi of square root of 2 dt. Since square root of 2 is constant, this evaluates to 4 pi times square root of 2. This makes sense intuitively. In each turn of the helix, we travel once around a circle of circumference 2 pi, while also moving up a distance of 2 pi along the z-axis. Using the Pythagorean theorem, each turn has length 2 pi times square root of 2, and we make 2 complete turns. Now, let's learn about curvature, which measures how sharply a curve bends at each point. The curvature kappa of t is defined as the magnitude of R prime of t cross R double prime of t divided by the magnitude of R prime of t cubed. Here, R double prime of t is the second derivative of R of t, and the cross product R prime cross R double prime has magnitude equal to the area of the parallelogram spanned by these two vectors. Intuitively, the curvature is large when the curve bends sharply and small when the curve is nearly straight. For example, a straight line has 0 curvature everywhere, while a circle of radius R has constant curvature 1 over R. Let's calculate the curvature of our helix example. We already have R prime of t equals negative sine of t cosine of t, 1. Taking the derivative again, we get R double prime of t equals negative cosine of t, negative sine of t, 0. Now we compute the cross product R prime cross R double prime. Using the determinant method, we get sine of t, negative cosine of t, 1. The magnitude of this cross product is the square root of sine squared of t plus cosine squared of t plus 1 squared, which simplifies to square root of 2. Since the magnitude of R prime of t is also square root of 2, the curvature is square root of 2 divided by square root of 2 cubed, which equals square root of 2 divided by 2 times square root of 2, which equals 1/2. So our helix has constant curvature equal to 1/2. This constant curvature makes sense because a helix bends uniformly as it wraps around the axis. Now let's talk about motion in space, where we interpret t as time and r of t as the position of a moving particle. The velocity of the particle at time t is given by v of t equals r prime of t, which is the derivative of the position vector. The speed of the particle is the magnitude of the velocity vector, v of t equals magnitude of v of t. The acceleration of the particle is a of t equals v prime of t equals r double prime of t, which is the second derivative of the position vector. In this model, the particle traces out our space curve as it moves through three-dimensional space. The velocity vector is tangent to the curve, while the acceleration vector generally has components both along and perpendicular to the curve. Let's apply these concepts to our helix example. Imagine a particle moving according to the position function, r of t equals cosine of t, sine of t, t. The velocity of the particle is v of t equals r prime of t, which we calculated earlier to be negative sine of t, cosine of t, 1. The speed of the particle is the magnitude of v of t, which we found to be square root of 2. Since this is constant, the particle moves at a constant speed along the helix. The acceleration of the particle is a of t equals r double prime of t, which is negative cosine of t, negative sine of t, 0. Notice that the acceleration has no component in the z direction. This means the acceleration vector is always perpendicular to the z-axis, pointing toward the axis of the helix. This is typical of uniform circular motion combined with constant speed vertical motion. Let's summarize what we've learned about vector-valued functions and space curves. A space curve r of t lives in three-dimensional space and is defined by three component functions. Arc length measures the distance along the curve and is calculated by integrating the speed. Curvature kappa measures how sharply the curve bends at each point. In kinematics, we interpret the curve as the path of a moving particle, with velocity v equals r prime, acceleration equals v prime, and speed as the magnitude of velocity. These tools let you analyze both the shape of curves and the motion of particles in space. Through our helix example, we've seen how these concepts work in practice, calculating arc length, finding curvature, and analyzing motion along the curve. Thank you for watching this lecture on vector-valued functions and space curves.